let's get started with Chapter 2. As I told you in class, Chapter 2, Chemistry, tends to be one of the biggest struggles for anatomy and physiology students. We're going to go to a lot of detail, but I want you to know that if you know a basic understanding of chemistry, you will be fine in this anatomy and physiology class. So don't. And it is important for understanding chemistry and biochemistry. That was going to help to understand a lot of medicine from many different angles, treating dehydration and fluid loss, understanding why IVs are supposed to be a certain, and why a certain molarity, why tests are within a certain range. That it all comes down to chemistry. So the body's made up of many different chemicals. Chemistry is going to underlie all our physiological reactions, from movement to digestion to the pumping of the heart to the nervous system. And we'll get into details of each of those systems as we go through. We can look at chemistry in many different ways. One of the most common ways to look at chemistry is to break it down into basic chemistry, kind of stuff you do with chemistry set you got as a kid, and then biochemistry, that chemistry that specifically relates to the chemistry that's going on in biological systems. And for us, that biological system is still the human. So let's start with basic chemistry. First thing we have to learn is that there are two things that make up the entire universe: matter and energy. Matter, you're very familiar with. It's anything that has mass and occupies space. We can see it, smell it, feel it. Weight would be mass plus the effect of gravity. We don't need to get into that fine detail. Matter can come in three different possible states, actually four, but solids, which have a definite shape and volume; liquids, which have a changeable shape. They take on the shape of whatever container they're in, but they still have a definite volume. So if you spilled a liter of Coke on the floor, it would spread out more, but it would still be a liter of Coke. Gases, on the other hand, have changeable shapes and volumes. Gases take on both the volume and the shape of the container they're in. So if you had a liter of oxygen and you opened it into an open room, you would now have as much volume oxygen as there is in that room, and it would be the shape of that room. The fourth state of matter I alluded to is plasma, but that's a superheated gas, and superheat and life don't go together, so we don't ever deal with plasma. But I'm sure you know what solids, liquids, and gases are. Energy, the other thing out there in the universe, is something that's capable of doing work, which really means putting matter into motion. Energy doesn't have mass. It doesn't take up space. If I turn the lights on and the light comes down and hits you, you don't feel it. You sense it, but you don't feel it. The more work that is done, the more movement that occurs, the more energy is used up. So here's a video. Hopefully this works. Whoops. Let's try this one more time.
Energy is the capacity to perform work. Potential energy is energy that is stored. Kinetic energy is the energy of motion. Energy is neither created nor destroyed, but converted from one form to another. This property is called the conservation of energy. The bow and arrow start out with low potential energy. As the archer's arm pulls back the string, kinetic energy from the arm's motion is converted to potential energy in the tense bowstring and arrow. When the bowstring is released, the stored potential energy is converted into the kinetic energy of the moving arrow. When the arrow hits the target, its motion ceases. If energy is neither created nor destroyed, where did the energy of the flying arrow go? Let's rewind and look at kinetic energy in more detail. When energy is converted from potential energy to kinetic energy, some of the energy can be used to do work, but some energy ends up as heat, a type of kinetic energy. Heat is the random motion of atoms and molecules. As the arrow flies through the air, heat is generated by friction between the arrow and air molecules. When the arrow strikes the target, all the energy becomes heat energy. The heat energy is rapidly transferred into the air and spreads out. Heat energy is a very disordered kind of energy. It has the highest amount of entropy, or disorder, of any kind of energy. Where do our muscles get energy to perform work, such as pulling back a bowstring? Our bodies use the chemical energy from food to perform work. Chemical energy is a form of potential energy. When your body breaks down food molecules, the stored potential energy from food can be converted to kinetic energy. The stored chemical energy in food is released in your muscle cells during the process of cellular respiration. Using oxygen, cellular respiration converts chemical energy from food to another form of chemical energy called ATP. Water, H2O, and carbon dioxide, CO2, are byproducts of cellular respiration. The potential energy of ATP can be converted to kinetic energy. Some of the kinetic energy is used to do useful work, such as pulling back a bowstring, but the heat energy that is generated cannot be used to do work.
Okay, so that's a little bit about energy. So they did say kinetic energy. There's two kinds of energy. There's kinetic energy, which is energy in action, and potential energy, which is stored or inactive energy. What you need to keep in mind, though, is that we're going to talk about different forms of energy: chemical, mechanical, electrical, and each of those has its own types of kinetic and potential. So energy can be transformed from potential to kinetic, can be transferred from one form to another, chemical to mechanical. Each time it is transformed, each time it's changed, the second law of thermodynamics tells us that some of that energy is lost. And for us, that means in the form of heat. So again, there are forms of energy: chemical, electrical, mechanical, and radiant. Chemical, we're going to talk about, will be the energy stored in chemical bonds, the relationship between electrons and atoms. Electrical energy is the movement of charged particles. We often think of electricity as the movement of electrons through wires, but in the body it's generally not going to be electrons, it's going to be things called ions. Mechanical energy is directly involved in the moving of matter, while radiant energy travels in waves and with heat, light, ultraviolet light, and X-rays are good examples of radiant or electromagnetic energy. Again, for each of those forms, there are potential and chemical. So this is the big problem we have with energy, or this is the reason that energy can't be recycled the way that matter can. Energy can be converted from one form to another. A lamp converts electrical energy into heat energy, and the heat energy makes the filament glow and makes light energy. But conversions are very inefficient. That second law of thermodynamics says that some energy, and actually it's most of the energy, is lost in the form of heat. It doesn't do the work that we want it to do. The other side of the universe is the things that energy works on. That's matter. And matter is made up of atoms and elements. Elements can't be broken down into simpler substances by ordinary chemical methods. There are 92 naturally occurring elements. I think there's 117 or so on the periodic table. Anything above 92 is man-made. But for us in human anatomy and physiology, really in biology, there are 4 elements that make up 96% of our body: carbon, oxygen, nitrogen, and hydrogen. I often remember it as carbon, hydrogen, oxygen, and nitrogen. And then you have the acronym CHON, C-H-O-N. You add another 9 elements to that, that's 3.9%. So you're almost at 4, or almost at 100%. And then another 11 elements make up the remainder of the elements in the body. So even though chemistry is a very broad study, the chemicals involved in living material are rather limited, mostly carbon, hydrogen, oxygen, and nitrogen. Those elements are made up of atoms. Those atoms are the individual building block of each element. It's really a subtle difference between atom and element. The smallest particle that you can have of an element with that properties of that element. And it's those atoms that give elements their physical and chemical properties. On the periodic table, there is an atomic symbol for them. It's either a 1 or 2 letter chemical shorthand. O is oxygen, C is carbon, H is hydrogen, N is nitrogen. If there are 2 letters, the second letter is lowercase. One of the issues with the periodic table is some elements get their name from Latin, such as sodium is for natrium. And K is potassium for selenium. So here's table 2.11, and I recommend you go read that in your book. Check it out. I won't read through the table for you. It's properties of oxygen, carbon, hydrogen, and nitrogen. Here we have the other 9 common ones: calcium, phosphorus, potassium, sulfur, sodium, chlorine, magnesium, iodine, iron, and then some trace elements. An atom is made up of the 3 subatomic particles that make up the whole universe. Protons, which have a positive charge and a mass of 1. Neutrons, which have no charge and a mass of 1. Electrons that have a negative charge, and for all intents and purposes, they do not have any mass at all. They are pretty much energy. In an atom, the number of protons is balanced by the number of electrons, so you have the same number of plus charges as you do minus charges. So an atom is atoms are electrically neutral. Protons and neutrons are found in the nucleus, while the electrons orbit the nucleus. And there are a couple of different ways you can model the electrons going around the nucleus: the planetary model and the orbital model. In the planetary model, which is simplified and is outdated because it doesn't fit with the known experimental data, it puts electrons in fixed circular paths, which we call, of course, orbits, to confuse it with the other model, orbital model. But the planetary model says that those orbits are like the planets moving around the sun. It's again, simplified and outdated, but if you can remember the planetary model, you'll have enough knowledge for this course and many other courses as well. The orbital model is a more correct model. The orbitals are now regions of probability of finding an electron. They're not fixed orbits. They're not circling the same pathway. So we use shaded regions to show where they're most likely to be. And it does work very well for making predictions of behavior of atoms for much of the experimental evidence we have. But it is a fine-tuning of the planetary model. So here is our orbital model and our planetary model. For illustrations, the planetary model works much better than the orbital model. Elements are defined by the number of protons that they have. Hydrogen has 1 proton, no neutrons, and 1 electron. Helium has 2 protons, 2 neutrons, 2 electrons. Lithium, element number 3, has 3 protons, 4 neutrons, 3 electrons. So these give us the things such as the atomic number, the atomic mass, isotopes, and atomic weights. So here are the 3 smallest atoms: hydrogen, helium, and lithium. Protons in red, neutrons in gold, electrons in black, in a planetary model. So the first thing we want to know about is the atomic number. The atomic number is the number of protons in the nucleus. On the table, it's often written with a subscript to the left of the atomic symbol, so lithium would be 3 lithium. The mass number is the weight of the atom, and that would be the number of protons and neutrons. Remember, the electrons don't weigh anything. So in the case of lithium, that would be 7, 3 protons, 4 neutrons. And we would write that as a superscript on the left of the atomic symbol. Isotopes are variants of the same element. That element always has the same number of protons, but sometimes the number of neutrons can be different. There are 3 different kinds of hydrogen out there, for example, but they're still hydrogen because they have 1 proton in the nucleus. That means the isotopes behave just like the regular atom. Binding and chemical bonding are all the purview of electrons, not neutrons. So isotopes do have some uses for us we'll talk about a little later. Atomic weight is the average mass of all the isotopes, which is why in the periodic table you don't get whole numbers for atomic weights. So here are those 3 hydrogen ones. There's hydrogen with no neutrons, deuterium with 1 neutron, and tritium with 3 neutrons. They all behave chemically exactly the same as hydrogen with 1 neutron. The deuterium and tritium are isotopes. And they are also what we know of as radioisotopes, isotopes that decompose spontaneously. They release radioactive energy. Sometimes it makes them become a different element. As they decay, those subatomic particles are being given off and they're released as energy, which we call radioactivity, and we have devices that can measure radioactivity. So we can use radioisotopes because we can detect them and they chemically behave just like the regular atom. So we can use them for biological research, and we can also use them for medicine. They release radiation. We can use that radiation to damage cells, such as cancer cells. We can use them for imaging. The other thing, though, is that radioactivity can also cause cancer. So radon in your home causes lung cancer. All right, I'm going to stop there.